Okay, we're going to talk now about micronutrients. The first lecture here will be a bit of an overview of all of the micronutrients. Need to think about and just revisit as a review that there's 17 total essential elements to plants. 3 are, of course, these non-mineral nutrients, carbon, hydrogen, oxygen. 6 are macronutrients, which we've covered up to this point, NPK, sulfur, calcium, and magnesium. And now on to micronutrients, and there's 8 micronutrients, so there's quite a few, and they can be kind of tricky to all keep track of. So they're listed here: iron, zinc, manganese, copper, boron, chloride, molybdenum, and nickel. And also talk about 5 beneficial nutrients. We'll talk about that, some of these a little bit next lecture: cobalt, sodium, silicon, selenium, and vanadium, and talk about some of those. But those are, again, this definition of what's essential. The 17 listed here are just that. They're essential for a plant to complete its life cycle. These 5 beneficial elements might provide some benefit or some added kind of indirect benefit, but plants can get by without them. Okay, so again, plants are mostly products of carbon dioxide and water via photosynthesis, and you can look at these macronutrients or secondary nutrients and the concentration ranges, and you've seen this graph many times this semester at this point. But let's just kind of think about this in terms of percentages. So nitrogen and potassium maybe somewhere between 1-2%. Then we get into calcium at maybe 0.5%. Magnesium and sulfur about 0.2%. Now let's talk about the concentrations for the micronutrients. Okay, so again, we've got 8 of them here. In terms of the elements, we've got nearly all of them exist in this kind of ionic forms, and the form that they're taken up by plant. We can see in terms of the major source, precipitation, salt, soil minerals, soil organic matter, so they can kind of come from a number of sources. But if we look at kind of down this list, iron, soil mineral, manganese, soil mineral, zinc, both soil mineral and organic matter, a lot of kind of the major source in terms of where plants get them does come from kind of that mineralogical fraction. So, and we can see just with a few exceptions, organic matter here, boron and copper. If we look at the concentration in plants, we can see kind of this is kept in percentages. Most times you'll see micronutrients reported in kind of a part per million, and ppm is really it's a 1 over, instead of a percentage of 1 over 100, say, a part per thousand, a part per 10,000 is 1 over 10,000. So we can see that I just list here in percentages to give you an idea of the magnitude in terms of how many coppers or borons or molybdenums or nickels there are for every, say in the context of nitrogen. So many orders of magnitude more nitrogen atoms in a plant than we'd find, some of these micronutrients. So we call them micronutrients, of course, because of the concentration, the relative abundance that they occur in plants. So, and it's not to say that they're not important. So, again, this is just underscoring that micronutrients are classified because of concentration, not because of plant importance. All 8 of these guys are essential for the plant to fulfill its life cycle. Okay. And so, because there are 8, we can have different ways to think about them or different ways to classify them, and they can be classified into cations or anions. So this is one example. The cations: iron, zinc, manganese, copper, and nickel. The anions: boron, chloride, and molybdenum. We can classify them versus organic and mineral sources. So the primary source is the inorganic, or that mineral fraction that we've talked about most of the semester. And there's 5 of those, as that table indicated: iron, molybdenum, nickel, and chloride. The primary source is your coming from that organic fraction, so this would be kind of synonymous with the nitrogen and sulfurs in terms of primarily cycling through that organic fraction. That's boron. And then two elements where they are relatively the relative importance of the inorganic and the organic fraction in terms of cycling availability to crops or plants is relatively evenly distributed, and then those are copper and zinc. Okay, so you know, similar to the macronutrients that we've already discussed, micronutrients can be primarily driven by the inorganic cycle, i.e. the mineral cycle, or the organic cycle. So tri-state recommendations, and we try to balance a little bit. This is going to talk some about the more practical management of micronutrients. We'll get into the individual micronutrients in the next lecture. But from a practical management perspective, tri-state recommendations state that most soils in Michigan, Indiana, and Ohio contain adequate quantities of micronutrients. So field crop deficiencies of chloride, molybdenum, and iron have not been observed in this region. Okay. Some soils, however, may be deficient in boron, copper, manganese, and zinc. So this is essentially a direct quote from the tri-states. Now, is this true with all crops in the tri-state regions? No, probably not. There's probably some specialty crops that are more sensitive to this, but part of this is crop nutrient requirement, but also just in terms of the soils themselves. And for the most part, again, in Ohio, in the tri-state region, we have relatively young, productive soils, and so micronutrient deficiencies typically are not that common, believe it or not. In instances where you will find micronutrient deficiencies are more likely to exist, and this is again a table originally from this tri-state published in 1995, and here's what they say. They say, for example, boron deficiencies, you're most likely going to find them in sandy soils or highly weathered soils that are low in organic matter. The crops that are most sensitive to boron deficiency are alfalfa and clover, so these legumes. Okay. For copper, you're going to find them. Copper deficiency is going to most commonly occur in acidic peat or muck soils with low pHs, less than 5.3, black sands, for example. The crops that are most sensitive to copper deficiency are primarily small grains, so wheat and oats, and sometimes corn. Okay. Manganese. Manganese deficiency most commonly occurs in peats and muck soils. So again, these are organic. Either there's a lot of organic matter or there's a little, not enough organic matter. And in the case of manganese, it's peats and mucks, these high organic matter soils with relatively higher pHs. So pHs are greater than 5.8. The crops that are most sensitive to manganese, primarily soybean. This soybean is the biggest, at least in our area. It's what we see most commonly. Micronutrient deficiency is soybean and manganese. Okay. Sometimes in wheat or oats, these small grains, sugar beets and corn have cases have been observed. And then zinc. Zinc deficiencies are primarily going to occur in peats, mucks, and mineral soils with pHs greater than 6.5. And by far the most common reported deficiency of zinc is in corn, but soybeans can also have some deficiency. So this is work that was, again, published in 1995, and today we still believe this, that not much has changed in this regard. So it's relatively old information, but it's still very relevant today. Okay. So for how do we determine micronutrient deficiencies? What are the diagnostics that we have? Well, we have both plant soil testing and plant analysis. Of those, plant analysis is most likely going to be more insightful or a little bit helpful for detecting micronutrient deficiencies than soil analysis. And we'll talk a little bit about that in a second. Again, this is this table 24 from the 1995 Tri-State, soon to be updated. But we can see that we've got these sufficiency ranges for some of these key micronutrients listed in part per million, not on a percentage basis, but in a part per million basis. Okay. Now, soil testing for micronutrients is not as reliable as plant analysis. But one of the really important things that soil testing can do is give you an indication of pH. Well, reports pH, and that can really help provide some context in terms of where micronutrient deficiencies might be. Okay. So this giant paragraph of text is from a micronutrient fact sheet that we recently published. And it kind of dives into some of the issues with diagnostics. So if you're interested in this, I recommend that you kind of look this up. But really, the original Tri-States suggest that soil tests for micronutrients are done with one of two extractants, either a 0.1 normal HCl or a 1 point normal HCl extractant. Okay, so these are kind of like the standardized and vetted procedures for detecting micronutrient deficiencies. Well, we've already talked about how we've moved from 2-malic-3 extractant from Bray P and ammonium acetate. So 2 extractants to get P and extractable potassium, and move to 1 in malic-3. Well, this represents potentially a third different extractant that you would use for micronutrients. And commercial soil testing labs really, I don't know of any of them that do this on a routine basis. So by far, when they're assessing micronutrient deficiencies from a soil test, they're going to be using a malic-3 extractant. And the problem is that we don't really know how universal or how effective malic-3 is as an extractant for micronutrients. So we've tried to evaluate this, and we've tried to calibrate malic-3 with DTPA, for example, but it's very difficult. And one of the primary reasons that we have a hard time understanding this or knowing what this means is that yield responses, when we go out and put out field trial after field trial and try to evaluate micronutrient deficiency and find a crop response, a yield response, for example, to micronutrient fertilization, it's very rare that we can actually find that. So it might be spotty or patchy in a field, in a depression or a knoll, for example, where we find some of this show up. But seeing this kind of across an entire field consistently, going out and measuring, overlaying a field trial, and trying to find a yield response is very tricky. So, and this is really a major limitation in terms of developing proper diagnostics. Here's an example of this. We've got malic-3 on this y-axis and DTPA as an extractant. We've got copper, manganese, and zinc. Well, you can see for some relationships, DTPA or a point HCl or 0.1 or 0.01 HCl in the case of the Tri-States has a very good relationship with malic-3. So DTPA extractable zinc and malic-3 zinc has a pretty good relationship. But then when we go to manganese, the relationship totally falls apart, and it's a pretty poor relationship. This is data that's taken across a number of states in the Midwest, looking at micronutrient deficiency in soybeans. Thinking about mobility, another way we can diagnose micronutrient deficiency is this kind of binary of, is it a mobile nutrient in plants or an immobile nutrient in plants? And so really the micronutrient deficiency that's going to occur in older leaves first is primarily molybdenum, and then everything else is going to occur in new leaves because it is a immobile nutrient. And so this is one of the kind of the key features, or a nice thing to kind of file away in your brain and thinking about micronutrient and diagnosing it, or at least cluing in a micronutrient deficiency, is that it's primarily going to be a newer, it's going to be deficiency symptoms that show up primarily in younger leaves first. And we can, I'm just showing you this flow diagram that you've seen numerous times as kind of a metric or as an indicator for that. And then this is an important graph just to kind of think about and consider looking at micronutrients and the relationship of micronutrients to pH. So we think of pH management is one of the first and primary things that you can do for micronutrients. And a lot of times it might be a little counterintuitive, but most micronutrient deficiency occurs when pHs rise above normal, above neutral, above 7.0. And so, particularly on organic or muck soils, when we have higher pHs than normal, we can induce micronutrient deficiency. So over applications of lime, for example, you might find micronutrient deficiencies in those scenarios, or just even in calcareous soils where pHs are naturally occur, say above 7. So our lone detractor of this trend is molybdenum. You can see molybdenum availability increases with pH, or availability decreases with decreasing pH. But most micronutrients are going to be more available, more acidic it is, and as that acidity increases, availability is going to decline. Okay, and so that's why it's thinking about pH is it's important to manage and keep between our targeted range. And again, we're typically shooting for something between 6.0 and 6.8 for most crops in general. Not all crops, but most crops, field crops in particular. But even vegetable crops, vast majority of vegetable crops, we're going to be managing in that range because that's where we're going to essentially maximize the most. It's like not the way to optimize any given nutrient, but it's the way to optimize or maximize the availability of all nutrients collectively. Okay, so that's the idea. But pH is very, very important. You go into a field and you suspect manganese deficiency, you pull a soil test, its pH is, say 7.8, and this is an area or a county where there's typically not a lot of soil acidity. Most soils, say, are trending it's below 7. Well, there's some indication that you might have manganese deficiency if you're seeing classic symptoms and your pH is kind of out of whack. So again, this is a really important indicator for diagnosing micronutrient deficiencies. Crop response to micronutrient fertilization in Ohio. So this is again a fact sheet that I alluded to earlier. The link to it is listed here. We went back and kind of painstakingly scoured every piece of information over the last 40 years that we could find in Ohio that conducted micronutrient trials. We found a total of 194 trials that have been conducted by Ohio State University. And of those 194, there was 9 documented cases for micronutrient deficiency. All of them were in manganese and soybeans. And typically those happened in fields with high pH. And so this doesn't mean that micronutrient deficiency doesn't exist. It just means that the take home for me is that it's just not widespread. And we've done some recent evaluations, not extensive, but we have done recent evaluations that go into this fact sheet. So there's a lot of work that's been done in the last, say, 5 years. But we just don't see widespread symptoms of this. And we juxtapose that, or this fact sheet, with what is common practice, and there's a tremendous amount of micronutrient fertilization that occurs. And we can think about, we always have to recognize, just because we don't see a yield response, an actual improvement in production of biomass produced by the plant, say if it's a grain or if it's a, whatever that reproductive effort that we're harvesting, or if it's not an agricultural crop, just total increased photosynthetic output, right? So total carbon accumulation would be a metric of increasing our seeing a yield response. And just because we fertilize and don't see that doesn't mean that there's absolutely no benefit that's being seen. So there's no, in an agricultural context, there's no economic benefit to fertilization. But we can think about other potential benefits. For example, the nutrition benefit if we're increasing micronutrients. That's of course a topic of a lot of interest lately. We know that our food is essentially less nutrient dense than it was 30, 40 years ago, primarily because of plant breeding, and so people are really wanting to increase micronutrients. But this is all from kind of a scientific perspective. It's unless we're getting into specific food science and it's all kind of speculative, right? We know that we just have not seen this phenomenon where crops need to be fertilized consistently with micronutrients. But we go into, you go and talk to growers, and you find out who's actually fertilizing with micronutrients and who isn't. There's quite a bit of micronutrient fertilization that occurs. I would argue, from a yield perspective, at least from a very basic field crop agronomy perspective, the vast majority of that micronutrient fertilization is not needed, and it's not paying the farmer back. But it's relatively inexpensive and provides a insurance, or provides some kind of peace of mind for that grower. But do they need it? Well, that's a question of a debatable question. For the data that we have, the evidence that we have, certainly don't suggest that they do. So is it something where the grower's seeing added benefit, or is it just kind of a marketing ploy, and there's this add-on kind of quote-unquote warranty package that a lot of fertilizer retailers are selling? I'll leave someone else to comment on that. I'm not going to say, but I want to point you to another fact sheet of sorts. It's an extension publication from the North Central Region, Iowa State University, with the second link, and this is an excellent resource. But we alluded to today with the DTPA and the malic 3 extraction, that graph. This is results from their field trials. They looked at a lot of field trials across, I think, 3 or 4 different states. You can see the numbers here, and you can see 88, 56, 88, 99, and then the number of trials with a yield response, and they had one. And here's the measured range in the soil test, so large ranges of extractable micronutrients, and here's where the recommendations said that they should be, and then based on that, here's the number of trials where yield increases were expected. And so that likely means that there's some wiggle room with zinc, because there's 24 yield increases expected and 0 found. So this is for soybeans specifically, but this is data that's very difficult and expensive to generate, and to do it kind of like widespread as this study was done, and to find so few responses is a bit maddening, to be perfectly honest. And it just shows, it just builds this body of evidence that widespread micronutrient deficiency is not a problem. And we probably, if we want to optimize agronomic practices, we're not going to need to fertilize every field with micronutrients to make that happen. So, okay, I've beaten that horse enough. I'm going to end there, and we'll pick up the next lecture with some specifics about micronutrients. Thank you.